All right, hello AP Chem students, welcome to topic 4.2, net ionic equations. The learning objective here is 4.2.a. Represent changes in matter with a balanced chemical or net ionic equation. For physical changes, for given information about the identity of the reactants and or product. And 3, for ions in a given reaction. Sorry about the weird capitalization on my Roman numerals there. Okay. Net ionics are really important. You're going to have to do them several places on the AP exam. So be sure that you understand this. They also really tie very heavily into pretty much everything moving forward. So vocabulary of chemical equations. Most of the time in chemistry, the first piece of information you need before doing any kind of analysis is a chemical equation. And so let's just review the parts of a chemical equation. So if your equation is this one, then what we would have here is your reactants and your products. Now, this is an unbalanced equation. So to balance it, we would add subscript. So let me just do that real quick. Okay, so now I have a balanced equation. So what I had to do was I had to make sure that I had the same number of each kind of atom on each side of the equation. So I needed two CuCls because over here I had two Cus. So I need to balance the Cus. And then here I needed two HCl's because that will now balance my two Cl's. And also I had two H's over there. So this is a pretty straightforward one to balance. Sometimes they get more complex, but it's really just a matter of practice. So balancing is not something that is taught in most AP chemistry classes. It's kind of assumed that you've had this in previous courses. If this is unfamiliar to you and you need some practice, there's a really good FET on balancing and lots and lots and lots of practice online, lots of really good videos on balancing equations. So let's look at some more meanings of symbols in chemical equations. So this S in parentheses stands for solid, means that species is in the solid state. L would be liquid, we don't have any of that in this equation. G would be gas. AQ means it's aqueous, which is dissolved in water. And then the arrow is yields. And we'll pick up another couple of symbols as we move forward through the course, but this is what we need right now. So both physical and chemical changes can be represented by equations, and in all cases the equations need to be balanced in terms of a few things. First of all, mass. That's a requirement called the law of conservation of mass. So we have all the total mass on the reactants is equal to the total mass on the products. You need to be balanced in terms of the number of each type of atom. That's what we were just looking at. And charge. And this might not seem obvious at first glance, but you're going to see as we move forward a little bit, especially in Unit 4, that this is actually really important. So there are three forms of chemical equations that can be used to represent reactions. They can each be useful given the particular situation and the information that you need about the system. So, let's look at all three of them. So they're the molecular equation, the complete ionic equation, and the net ionic equation. So I've shown you an example using lead nitrate plus potassium iodide, which is a classic example that forms a precipitate. And so here's your precipitate of lead iodide. We're going to talk more about precipitates again as we move forward. But the molecular equation, this is probably what you're most used to seeing. This is kind of the traditional way of writing a chemical equation. So all species are present in molecular form, and that's really used to show species as they're found as reagents. If you're going to make these solutions from scratch, when you pull the bottles off the shelves, these are the ways the formulas will be written. So then if we look at a picture of this reaction, here it is. Okay, so in this flask up here, we might have lead nitrate, and then in the beaker, we already have potassium iodide, and then this yellow solid is being formed as the PbI2. Now the KNO3 is being formed as well, kind of. Okay, so let's talk about what I mean by kind of, because actually it's not really. So what it looks like here is that the compound KNO3 is being formed, and actually that's not what is happening. What's actually happening is that in your beaker here, you've got the potassium ions and the iodide ions that are dissolved in water. They're aqueous. So they're spread out from each other, like we see represented here. Also in aqueous form is your lead nitrate. So in this flask up here, where it's being poured in, you have the lead ions floating around, the lead 2 ions, and then you also have 2 nitrate ions, and those are proportional. So then once these two things are combined in the beaker, what's actually happening is nothing. to your potassium and your nitrate. So the potassium is starting out as dissolved in water and ending up dissolved in water. And the nitrate is starting out dissolved in water and ending up dissolved in water. However, they are still there. And initially they're separated from each other, right? Because here the nitrate is in this flask and here the potassium is in this flask. And so they are mixing together, but they're not forming a compound in that they're not attracting to each other and clumping together because they're staying dissolved. So in the complete ionic equation, this is pretty clear. So all aqueous species are represented as ions, and that's used to show all species as they're found in solution. So in the solution, though, remember that we've got this solid, and so we need to show that, and we do. This PbI2 is marked with an S. And then, of course, if we let this sit over time, that solid would settle. So then the net ionic equation is sometimes really helpful to think about because it shows all the species that are breaking or forming bonds. So basically anything that's undergoing chemistry. So if you think about it in this way, this potassium and the nitrate up here in the complete ionic, they're not really undergoing any chemistry. And that's why we call them spectator ions, because they're just kind of watching the chemistry that's happening. And so you can see that here we have, well, this is a slightly different representation. This is sodium and nitrate instead of potassium and nitrate, but it's the same idea. But then you've got this solid lead iodide down here, okay, and so this is all precipitated out. So this kind of situation here, if you want to think about what is changing, that's where a net ionic is really helpful. So the lead 2 plus your 2 iodides then make your lead 2 iodide solid here. So that's where a net ionic is really helpful. So all three of these have their place depending on the information that you want to get. The molecular, if you're trying to do stoichiometry, the molecular is going to be the most useful. And again, stoichiometry is something that we'll talk about later on in Unit 2. Again, the complete ionic is the best if you're trying to get a very complete picture of how everything actually is existing in your reaction container here. And then the net ionic is really useful for talking about exactly the chemistry that's going on. Bonds that are being broken and formed, that becomes the most clear when we're looking at the net ionic. So spectator ions, we've talked about those a little bit. So not all aqueous ions will take part in the chemical reactions. And the ions that do not participate, in other words, do not change from the reactants to the products, are called your spectator ions. And now it's important that you understand they do not change at all. They don't change state, they don't change charge, nothing changes, okay? In order to be a true spectator ion, nothing about them can change. They start and finish in the same way. So when we're writing net ionic equations, the spectator ions are not included. In AP chemistry, there are 4 ions that will always cause their compound to be soluble. And so as a result, they'll always be spectator ions. And they're easy to remember. It's a SNAP. Okay, so sodium, nitrate, ammonium, and potassium. So those are your 4 SNAP ions, I like to call them. If you see them, they are going to be dissolved along with anything that they're combined with. So these ions make anything soluble. So that sodium nitrate, of course, will be soluble because it has 2 SNAP ions. Sodium iodide would be soluble. Potassium nitrate would, well, of course, that's also got another thing there. But copper nitrate, like anything. You can make anything soluble if you have these 4 ions. All right, so tips for writing net ionic equations. When you're writing a net ionic equation, keep the following things in mind. Solids, liquids, and gases do not dissociate in net ionic equations, only aqueous. So only aqueous solutions are shown as ions. Remember that polyatomic ions do not dissociate in water, but they do separate from the ion that they're combined with. So for example, if you have nitrate, okay, we'll take that for a minute, the sodium nitrate, the nitrate will separate from the sodium, but the NO3 minus itself stays associated. The equation needs to be balanced in terms of both charge and number of atoms, as we've talked about already. And states are not required, but they may be needed if they're asking you to talk about a physical change. So let's just look at a couple of examples here. So write a net ionic equation that shows the dissolution of potassium dichromate. So first of all, this is a physical change because we're just dissolving, that's all. So we would write it this way. So you have solid potassium dichromate, and then it would split into its 2 ions. And so the 2 ions here are 2K plus because this is not diatomic or anything like that. This is just two of your Ks. And so when they dissociate, then that means you've got one going this way and one going that way, for example. And so that becomes a coefficient because they're no longer bonded into the same compound. And then you've got your dichromate. So again, as I mentioned in the previous slide, this is a polyatomic. So the dichromate itself will stay together, but it does separate from the ion that it was associated with to form the ionic compound. So let's check and see if things are balanced. So do we have our number of K the same on both sides? So we've got 2 here and 2 here. So check. Our number of dichromate, so we have 1 on the reactants and 1 on the products. So that is a check. And now let's look at the charge. So neutral on my reactants. 2 times plus 1 is plus 2. And then 2 minus is there. So neutral on the products overall. And so yes, our charge is also balanced. So now let's think about the net ionic for the white precipitate that's formed when barium nitrate is mixed with copper sulfate. Okay, so this is going to be a chemical change. NO3 minus is a spectator ion because of SNAP. Cu2 plus then is a spectator ion because it starts out the reaction as aqueous, and then because it cannot combine with the nitrate, because the nitrate will stay dissolved, it must also be stay dissolved, and so it will be a spectator ion. So then our net ionic, with things that are left behind, are Ba2 plus and SO4 2 minus, and those combine together to give BaSO4 solid. So let's check our balancing here. So 1 barium on the reactants, 1 barium on the products, so number of bariums check out. 1 sulfate on the reactants, 1 sulfate in the products, so that checks out. 2 plus 2 minus is neutral, and then this is neutral. So our charge checks out. Now, just to give you a hint, sometimes when I am writing a precipitation net ionic, I like to start with the solid and then go in reverse. Because I can think about, okay, so if I rearrange here, then my 2 options are barium sulfate and copper nitrate. I know it's not the copper nitrate because the nitrate's a spectator ion. A SNAP ion, which makes it a spectator ion. So then my product must be barium sulfate. So I write the barium sulfate first, and then I think about what it breaks into. That's just how it works for me, but you do it however it works for you. And so that's it. So what should I be able to do with this? Well, you should be able to write a physical change like dissolving using a net ionic equation. You should also be able to write a balanced net ionic equation for a chemical change that pays attention to both number of atoms and charge. And that is it. And I will see you soon for topic 4.3.